Hello, and thank you for joining me today. Uh, Today's lesson is going to involve some equations, some math. We're going to look at using the wave speed equation. And so at the end of this video, I want you to be able to calculate speed or velocity, frequency, and wavelength for a wave, given enough information to do so. So for starters, this is a slide we looked at on the last presentation. We're looking at the electromagnetic radiation, the electromagnetic spectrum. And so if we look at just the visible light spectrum, you'll notice that violet is down here with a wavelength of roughly 400 nanometers. Red is over here with wavelength of 700 nanometers. And so red has a longer wavelength and a lower frequency than violet does. And then our colors go in between. So the rainbow, colors of the rainbow is Roy G. Bouv because they've kicked out indigo. So red, orange, yellow, green, blue, and violet are all related to these frequencies and wavelengths. And that's why the rainbow looks the way it does in the sky. Now, while these are different colors, they have different frequencies and wavelengths, they all travel at the speed of light, which if you think back is 2.998 times 10 to the 8th meters per second, or for our equation is going to be 3 times 10 to the 8th meters per second. A lot of times I'm going to give you wavelength in nanometers, so you have to convert that to meters for the equation. Very important you have that in meters. And frequency is always going to be in hertz or 1 over seconds. And we'll do some practice with that today. So for starters, I want to know what is the speed of a wave with a frequency of 45 hertz and a wavelength of 2.34 meters. So to do this, we have our equation is, we're not going to use c this time because that's speed of light. So we use v equals frequency times wavelength. I know that the frequency is 45 hertz, and I know that my wavelength is 2.34 meters. So I have a frequency and I have a wavelength. So I can then solve for my velocity. So v equals 45 hertz times 2.34 meters. And if I take 45 times 2.34, I get an answer of 105.3. Oh, that wasn't supposed to happen. Equals 105.3. And then if I'm going to do this correctly, we're going to look at significant figures. I have 2 here and I have 3 here, so we're going to round this. I need 2 sig figs, so 1, 2. I'm going to look 1 to the right. The 5 rounds it up. I have a speed of 110, and this is going to be meters per second here. That would be my speed. Now, next one. I want to know the frequency of light that has a wavelength of 520 nanometers. So my equation, we're going to use c equals frequency times wavelength. The reason I use c is because I'm talking about light. We know that c equals 3 times 10 to the 8th meters per second. I'm looking, I can have a frequency and I can have a wavelength. In this case, I'm looking for the frequency, so I don't know that. My wavelength is 520 nanometers. If you think back, nano is a prefix that means 10 to the negative 9. So we're going to take 520 times 10 to the negative 9th to go from nanometers into meters. So if I take 520 times 10 to the minus 9th, your calculator is going to spit out 5.2 times 10 to the minus 7th meters. And then I can solve this equation for frequency. So I know if I divide both sides by wavelength, I get frequency equals c over lambda, speed of light over wavelength. That's going to be 3 times 10 to the 8th meters per second divided by 5.2 times 10 to the minus 7 meters. And my frequency is going to be 5.77 times 10 to the 14th. And because I only have 2 sig figs in this number, I have 5.8. times 10 to the 14th, and that's going to be hertz, or I can do 1 over seconds. Either one works. But there's going to be my answer on that one. And the last one, what is the wavelength of light that has a frequency of 5.36 times 10 to the 14th hertz? So again, I have the same equation, C equals frequency times wavelength. I know C is 3. I'm going to use E for times 10 to the 8th meters per second. Frequency is 5.36 times 10 to the 14th hertz. And I don't know my wavelength, so I can solve for wavelength by dividing by frequency. So I get wavelength equals 3 times 10 to the 8th meters per second divided by 5.36 times 10 to the 14th. And if I do that, I will get an answer of, oops, give me 1 second. If I do that, I should get an answer of 5.60 times 10 to the minus 7th. And my unit here is going to be meters, or I can call this 560 nanometers. Either one works, but that's going to be your calculations there. All right. Here is an opportunity for you to practice. So I want you to work through these. I have the answers on the next slide, so pause this video, work through these, and then when you hit play, you'll get your answers. And so here are the answers to the first ones. You should get 5.77 meters, 3 times 10 to the 18th hertz, and 20,000 nanometers, because I wanted this one in nanometers instead of meters. And then your last set of questions. So if you still want some more practice, here are some opportunities for you to practice. Pause the video and I'll give you answers on the next slide. And here are your answers to this one as well. So 7.06 times 10 to the 16th hertz, 588 nanometers, again wavelength in nanometers, and frequency 7.5 times 10 to the 14th hertz. There should be more significant digits there because I had 4 here. So you should have 4 significant figures on this number. So again, the energy change an electron goes through is proportional to the color of light. So if it's a lot of energy, it's going to be more of a purple color, a violet color. So higher energy has a higher frequency, which is our violet color. Lower energy has a lower frequency, which is our red color. So if you see purple light, you know there's a lot of energy being released. Red light, you know there's less energy being released. Just something to think about moving forward. Here's a reminder on how atoms emit light. So again, you absorb a quantum of energy, go from the ground state to the excited state. When it loses that energy and goes back to the ground state, the energy has to go somewhere. So it's emitted as a photon of light. And that was a quantum that was gained to jump from one to the other, but it emits a photon of light. If it was a large amount of energy, we get more of a violet color. If it's less energy, we get more of a red color. And so there's another time through that. So make sure you read through this. Make sure you're comfortable with how atoms emit light as well. Here are some final questions for you to answer. I thank you very much for your time and attention. Look forward to seeing you again in class and working through the rest of this unit. But enjoy the rest of your day, and I will see you next time.